welcome Professor Doudrick. He's an associate professor in the Department of Chemical and Environmental Engineering and Earth Sciences. His research focuses on problems related to physical, chemical, and environmental processes with an emphasis on water quality, drinking water treatment, and emerging contaminants. The presentation title today is Catalytic Membranes for Treating Contaminants in Drinking Water. Let's welcome Dr. Doudrick.
Great, thank you. You guys hear me okay? Sounds like it. All right, let's just dive right in here. I kind of want to open up, just give you a little background. I see a lot of some familiar faces in here, but I see a lot of unfamiliar faces too, so you may not know me. Yeah, behind the podium is kind of awkward. So I'll give you a little bit of an overview of what I do in my research group. So I like to focus on something called an emerging chemical contaminant. So an emerging chemical contaminant, I should probably step over here, I can hear feedback already, is essentially a contaminant that we know is harmful and we know it's present, right? We can measure it in the environment, but it's unregulated. Okay, there's many reasons why it would be not regulated. Oftentimes it's due to cost of treatment or unavailable treatment options. I could go on and talk about these things probably for an entire day. It'll keep me up at night. It should keep you up at night. Things like PFAS, pharmaceuticals, pesticides, etc., that end up in the environment. And I focus on physical chemical processes, and I think about this in two camps. So the first is what happens when it gets in the environment. Are we able to measure it? Can we measure it at lower levels, like nanogram per liter levels? What's its reactivity in the environment? And then where does it go once it gets in the environment? And then on the flip side, once it actually enters into our drinking water treatment plants, I like to think about new technologies for treating these emerging contaminants. So creating technologies that we don't have yet, so that we could potentially treat these. And today I'm going to focus on catalysis. So it might surprise you, or maybe not, but about 3 to 4% of the nation's energy is spent on drinking water and wastewater treatment. So a lot of energy goes in to drinking water treatment, and we spend roughly $4 billion a year just to operate these plants, right? So this cost doesn't even include chemical costs, capital costs, operator salaries, etc. Now the image here is what we call a conventional drinking water treatment plant. Some of you may have seen this before, you may have had a class on this before, especially if you're engineers. But the typical processes that we see in a drinking water treatment plant are disinfection, which I think most of us are familiar with. Coagulation, flocculation, and sedimentation are essentially to take the particles that are in our, for example, lake water, and then aggregate them together and settle them out. And then we have like a sand filter. That would be kind of a polishing step, right? So these are, this is historically, every drinking water treatment plant uses processes like this, and it works really well for ensuring that we don't get, for example, microbial contamination, okay? But when it comes to these emerging contaminants, none of those work, right? So the stuff that we're entering into our drinking water treatment plants, at this point in time, we don't really have any options to remove them, right? That goes back to one of the reasons why a lot of these contaminants that we know are harmful are unregulated, right? Because you can't regulate something if you don't have a treatment technology. So they're what we call recalcitrant, and they're just going to pass right through. So we need more advanced treatment processes, and that's the topic for today. So if you look at the infrastructure report card that the American Society of Civil Engineers puts out, yeah, drinking water's not doing so well, right? We're rated a D, so we kind of look to the future. We need a lot of money, and we need a lot of extra things like technologies in our drinking water treatment plant, and that's going to be expensive. So one of the, quote, technologies that I try to use is nanotechnology, which 20 years ago was a fancy term. Nowadays, it's just kind of an everyday term that we use. So how can nanotechnology help drinking water treatment? Well, the first thing is it can provide these new advanced treatment options, one of them which I'll talk about today. The second thing is it can allow us to treat the contaminants at a faster rate. In that case, we're going to save energy, we're going to save money. This is a pretty big one. We can reduce the footprint. So there's actually a company that has kind of these deployable systems. So this is like one of these cargo boxes, and they have essentially an entire treatment plant in these cargo boxes. And in a disaster situation, like a hurricane or earthquake, etc., they can deploy these and have like a mini drinking water treatment plant. And again, this requires types of technologies like nanotechnology to be able to scale down treatment plants. And then of course, energy, which I've written this in the energy, right? So we think about energy. This will allow us to reduce energy and chemical requirements. So we think about emerging contaminants. I've been working on oxidized contaminants for about 15 years. And in particular, the focus of today's talk will be nitrate and nitrite. So have you guys heard of these contaminants before? We heard of some of these? How about something like TCE? Or hexavalent chromium? Have you heard of hexavalent chromium? Right, so if you've seen Aaron Brockovich or Civil Action, those two movies were all about hexavalent chromium. It was the topic of the movie, or it was the movie at Water Week. I think it was last week, right? That we saw it. It might surprise you to find that we've known hexavalent chromium is a carcinogen for over 20 years, right? It's still unregulated in drinking water though. And they made movies about it, right? The main reason is we just don't have really good treatment technologies for this. So one of the technologies is catalysis, and in particular palladium-based catalysis. There's been a number of papers, reviews that came out that look at using palladium for treating all of these contaminants. In fact, palladium works really well, right? Palladium is a great catalyst for drinking water contaminants. So all of these contaminants, because they're oxidized contaminants, they need to be reduced. Okay, so palladium serves as a nice catalyst for reducing these contaminants. So nitrate. Here's some more maybe surprising information for you. Again, I'm going to keep you guys up tonight. Does anybody know what this is a map of over here on the right? St. Joseph County is where we live. So these little red and yellow dots are all private home wells that have been sampled for nitrate by the county. And red, you can barely see this, but red is greater than 10. Orange is 5 to 10. Okay? The EPA limit, okay, the EPA limit for this is 10. So all the red ones for the EPA limit are bad, right? So if you live in Granger, you probably have contaminated water, and you've been drinking nitrate greater than the limit. Now that's actually not that surprising for me, but it's also maybe not as scary as you think. The reason that is because the reason EPA limits this at 10 is for something called methemoglobinemia, which is blue baby syndrome. So unless you're an infant under the age of like 3 months, it's probably not an issue for you based on the risk assessed by the EPA. However, there's been new evidence for the past at least 30 years that shows that nitrate contributes to a lot of different cancers. The main one being colorectal cancer, where a study found that up to 82% of all colorectal cancers are caused by nitrate in drinking water and in food. Okay? They suggested a new limit of 1.4. 1.4. So if you have any yellow or red dot, you know, you may want to consider getting your water tested. Does anybody live in Granger? A couple people. Probably most of the non-students, I guess. So the Notre Dame has its own drinking water system. We use groundwater. No treatment is applied, so it just straight from the ground, right to the tap. That's why it kind of tastes a little nasty. Just for many reasons, we won't go into it. But you're not going to have the nitrate problem on campus. The reason you have nitrate problem in these areas here is because you have septic systems that are leaking into your own water. So you're not only drinking nitrate, you're drinking pharmaceuticals and whatever else you're peeing out, and it's entering into your septic system, which then leaches down. Yep. All right, I talk about that way too much. I tell you, I can get off on these tangents where I'll get on like slide 10, and it's like 30 minutes already. All right, so palladium. So why don't we use more advanced technologies like palladium? Well, again, it comes down to cost. So if you look at just the cost of palladium alone, the price has increased 20 times over the past 30 years. And it's going up even more now that Russia is having a conflict, and they're one of the main makers of palladium. So how can we reduce costs? Well, it comes down to better material design. So if we think about a catalyst, all the reaction happens on the surface. If we have a big catalyst particle, we're wasting all of the bulk center of the catalyst, right? So we want to try to decrease the size of our catalyst particles down to single atom or tiny, tiny little palladium catalyst so that we can hopefully use palladium. And then we think about, all right, well, what's the value of lowering our risk, right? So, you know, unlike electrical engineers or computer engineers or whoever else works in the industry, right? I can make a $1,000 iPhone and somebody's going to buy it, right? There's a demand for that. Okay, but what's the demand for drinking water treatment? I'm not going to be able to sell this kind of fancy technology because essentially it should be free, right? Drinking water treatment is a basic right, basic human right, health. And who's paying for that? Probably the taxpayers, and it has to be as cheap as possible. So just kind of touching on this more, what can nanotechnology do? We can change shape, we can change different material types, which allows us to increase the selectivity of the reaction and the reactivity. Again, as we decrease the size, we get more surface atoms, okay, and less bulk atoms. So we're using less palladium for the same reactivity. How does palladium work as a hydrogenation catalyst or a reduction catalyst? So the way we use palladium is we use hydrogen gas as a reductant. The hydrogen gas is split on the palladium surface, and then that hydrogen then reacts and reduces our oxidized contaminants. So nitrite, for example, we can actually reduce it to nitrogen gas, which is a harmless product, which is our goal. So with the catalyst, we get good contaminant destruction, it's fast, and we get selective control over the byproducts. But if we're realistic, most active catalysts like palladiums are too expensive. And unfortunately, other catalysts like iron, nickel, or whatever, they're just not stable in water. So we kind of have to stick with palladium. It's sensitive to aqueous conditions, meaning it can actually be fouled by whatever else is in the water, which reduces the activity. And we need to use nanocatalysts, but how exactly can we do that? So we think in an engineer perspective, from a practical perspective. One way is to use what's called a batch reactor or a slurry batch reactor. This is very simple. Just think you take a beaker, you put a powder in there, and you mix it around, right? That's simple. The problem is you get issues with hydrogen gas solubility. So if I'm just trying to bubble in hydrogen gas, the solubility is really low, so I'm very limited on hydrogen gas there. You can actually destroy the catalyst by colliding together. And then the worst part is you got to separate the catalyst somehow post-treatment. The more used one is something called a packed bed reactor. So in a packed bed reactor, we take our little tiny palladium and we load it onto a support and we pack this into a reactor. We trickle in the hydrogen gas and the water at the same time, and then out comes plain water. Poof, magic. So the good thing about this is the catalysts are immobilized, so we don't have to worry about separating them. It's continuous flow, so from an operational perspective, this is very nice to use at scale. But again, we have hydrogen limits. We have something called diffuse limitations, so this actually slows our reaction rate. And we have limit control over the design, and we actually find that we can get biofouling, which then just completely shuts down the system. All right, so this is where we come into the membrane reactors, and we're going to solve all these problems with these membrane reactors. So membranes are already used in drinking water treatment as a filtration device, right? Typically in a system like this where you have these little straws. So imagine a little drinking straw, and you're drinking the water, and the clean water, or the dirty water passes through the wall of the membrane, and then you get clean water out. So what we want to do is a very simple process where we take this wall of this membrane and we load it up with the palladium, okay? We flow hydrogen gas on one side in the gas phase. We flow our contaminated water on the other side of the membrane. The contaminant and the hydrogen diffuse into the membrane and react, and out comes our clean byproducts. So essentially, theoretically, this solves all of our issues that we have, right? We now have efficient mass transport, so we get a faster overall reaction. We're not limited by solubility. The catalysts are immobilized, and it's scalable. We've already got systems at full scale in drinking water treatment plants like this. There's still a few questions there that remain to be asked. So the project objective for us was to essentially take this hollow fiber membrane that we are going to pass hydrogen gas through, so gas transfer membrane, and we're going to put a catalyst layer on the outside and treat the drinking water. So how do we do that? Well, we were inspired by biofilm reactors that we use in wastewater treatment. So for these, you take these little hollow fiber membranes and you load a biofilm, or you let a biofilm grow on the outside, and the biofilm then interacts with the wastewater and treats the wastewater. So what it would look like, it looks like essentially this, where you have your hollow fiber membrane wall here, you have your biofilm, your contaminants in the water phase out here, that's diffusing in, hydrogen diffuses in and reacts to the biofilm. So what we made was essentially an artificial biofilm using calcium alginate. So alginate is a byproduct derived from brown algae. It's renewable, it's non-toxic. It's technically a biopolymer or a hydrogel. So it's highly aqueous, composed of up to 99% mass of hydrogen. It's easy to synthesize and control, and it's actually really effective for immobilizing particles in the structure. So for us, it was just a really nice natural way to coat these membranes and immobilize our catalyst. So the way we did this was we took hollow fiber membranes, we dipped it in alginate, we cross-linked it with calcium, and we loaded it with palladium. Okay? And the result was some actually pretty tiny palladium particles, roughly 2 to 6 nanometers, that were in our layer out here. Now, I hope you guys can see this. You can probably see this. But this is what the result is here. Can you see the kind of thinner, more transparent white line there? Probably hard to see that. That's the hollow fiber membrane. And then the black is the palladium coating on the outside. And then we made multiple fibers, we bundled them together, and we put these in a reactor, and we tested them. All right, so now we published 3 papers on this, so there's a lot of results, but I want to kind of hit some of the highlights here. And one of the main highlights was thinking about what's the effect of palladium loading? So if the density of palladium in that hydrogel layer on the outside. And the y-axis here shows the rate constant. So as we increase palladium loading, the rate goes up, as you might expect. But if we normalize that rate constant to the amount of palladium that we're adding, it actually goes down and comes to like this constant level. So what's going on here? How are we adding more palladium, but from a normalized perspective, we're not getting that use of palladium, right? The efficiency or the use efficiency of that palladium isn't great. So what we did was we took some little microsensors and we actually measured concentrations through the hydrogel layer. Right, this was a really fun experiment. So we used oxygen as a surrogate oxidized contaminant. And what you see here is, so imagine on the left here, you have the inside of the fiber, right? So this is where the hydrogen is. And on the right side, we have the water, okay? And then this dotted area is the catalytic hydrogel, right? So the hydrogen comes through and it diffuses into the catalytic hydrogel. And the oxygen will move through the water, diffuses through the outer layer here, and then comes into the hydrogel. And what we found was that, as you would expect, because of diffusion and reaction, the concentrations of oxygen and hydrogen decrease as they move through the catalytic layer. So if you look at this from a model perspective, it's much easier to understand. So here we have, again, oxygen moving through. This is at lower density palladium. This is higher density. And what we found was that with lower density, we get reaction occurring throughout almost the entire layer. But with a higher density, we were only getting reaction occurring at the surface. So we were only using that layer at the surface of the palladium. All right, how much time do I have left here? 8 minutes? Okay. I think I'll be able to cover this. So yeah, we were finding that it's based on how the reaction occurs in the layer itself. So you really need to have layer thickness control along with the palladium density that you have. So again, we're looking at a modeled reaction here where we have hydrogel thickness or the catalytic layer thickness. And then we have flux here, just think of that as reactivity. Okay, so at a really high palladium loading, you get a really high reactivity, as you might expect. But the optimal thickness shifts left, right? So if we can really just jam as much palladium as we can in this hydrogel layer, we really find that 30 microns is like the optimal thickness. Now, the problem is we don't really have any control over the thickness. We just kind of dip these fibers in there, and the layer goes on there, the hydrogel layer, and that's it. And I want to say, if I remember correctly, the actual layer is somewhere around 600 microns, right? So this is an issue for us. We don't have any control over the thickness, but we find that we have to have control over the thickness, okay? So we'll swing back around to that. I want to show you one more interesting result here on these catalytic hydrogel membranes. And that's the effect of those other things that were in the water that might reduce the rate of water treatment, right? So sulfite, bisulfite, and dissolved organic matter are the 3 main ones that we know react with palladium, right? So this is not specific to our system. It's just bad for palladium. But our thought was, well, maybe the hydrogel is going to provide some sort of protection to the catalyst, okay? Essentially what we found here, though, is if you look at these numbers, higher ratios are better and low is bad. So bisulfide was terrible. It's always been the worst one for palladium. It's a well-known thing, and the hydrogel did nothing to help us. So if you have bisulfide in your water, it would have to be removed first. I guess the interesting one, though, is the dissolved organic matter. Right? Normally that is really detrimental to a palladium catalyst if you just have the palladium in the water. But for some reason, the hydrogel was protecting the catalyst from DO and fouling, which for us was kind of promising. We think it may have something to do with size exclusion. It's kind of unknown at this point. All right, so what's next? What are we doing next here? Really, we're thinking about how can we optimize the thickness of the catalytic layer so that we can maximize palladium usage. We want to also decrease the size of the catalyst, right? 2 nanometers is tiny, but we want to go down to single atom. We're talking about way less than a nanometer. The most efficient size that you can get would be single atom. And then we also want to think about, all right, well, let's say we do get down to single atom, we get control over the thickness. Is that ever going to matter, right? Is it ever going to be cheaper than some of these other treatment technologies like ion exchange? And what are the trade-offs? Okay, so that's probably the main thing, because if it doesn't make sense from an economic standpoint, or even an energy usage standpoint, it's not going to matter. So this is some of the new work we're doing with Bill Phillips' group in chemical engineering. In fact, Angie over here is a grad student that's working on this, and these are her beautiful images. So the idea is that, all right, well, forget the hydrogel. Throw that in the garbage. We don't have any really good control over it. What if we just start from the ground up using polymer chemistry? We can take the hollow fiber and then create a engineered polymer on the outside that has specific sites that are specifically tailored for single atom catalysts, right? So we're kind of solving 2 of those things. So Bill is really good at making nanostructured membranes that have tiny, tiny nanometer pores, but you can put a lot of water through it, okay? So these pores are roughly 100 to 200 nanometers, and the reason that's good is because you have advective flow through these pores, and the diffusion links to the catalytic sites for the contaminant are tiny. What that means in a general perspective is that the reaction rate is going to be very fast compared to some of the other systems. And actually here is, Angie, do I got to click on this video for it to work? This is Angie making some of the membranes over in Bill's lab. So we've already started this. So we cast the membranes, and then we load them with palladium, and then palladium ions, and we reduce the palladium ions, and we get this little film disc membrane. And just kind of give you a little preview of the results. We're already getting rates that are way higher, orders of magnitude higher than what we saw with the hydrogel membrane, which in itself was already better than what we were seeing with just kind of like putting catalysts in water. So this is really promising for us, and we're going to continue on with this. Again, the end goal is to try to, that little disc is just like our test system. It's just the membrane, we put that in water. The goal, though, is to then coat a hollow fiber membrane and think about how we can scale up that process, and you'd have a bundle, and that bundle goes into a cassette, and that cassette goes into the water. All right, we got good time here. I want to show you the next piece. So if you guys aren't familiar with the career awards by NSF, half of it is research, but the other half is thinking about education. And I'll be honest with you, I think I wrote a pretty good proposal, but I think the only reason I got funded was because of the virtual reality stuff that I proposed in it. Which is usually the opposite. You usually get funded because of the research, and then the education is kind of secondary. I don't know. So I started this a number of years ago in collaboration with the Office of Digital Learning here on campus. And my thought was, it really came down to, I used to take my students that teach a drinking water treatment course, I used to take them to Chicago, to the largest drinking water treatment plant in the world. Okay, huge, 2 billion with a B gallons per day capacity. Right, so we would get a bus, cost like $1,000. We'd ship everybody out for take the whole day. We'd ship everybody out, we'd do the tour, we'd eat pizza, and we'd come back. Like the logistics of that is really difficult, right? Trying to get students up to meet at 8 a.m. on time, get there, everything has to go good there. You go get the pizza, that has to go good, and you get home. It's kind of a nightmare. In fact, the reason that I thought about this was the one year it was canceled. The morning of, 10 minutes before we got on the bus, the guy called me and said, "Oh, there's a water leak, and I'm gonna have to cancel because I gotta deal with it." Like he didn't understand, like, this is tough for us to get out there, right? So I was like, you know what, I'm gonna have to rethink this. So my thought was like, the tours are useful though. The students love the tours. You go, you get some hands-on, oh, I learned how to design this system, now I'm seeing the system in action. So I thought, what if I could take them there, but virtually, all right? So we created this virtual reality tour. All right, let me show you guys, if at the lunch break, if you want to try this out, you can come find me, and I'll be more than happy to set you up with the Oculus headset, and you can see this in a virtual space, okay? But it's not just a virtual space. Anybody can use this. Anybody can look at it. If you go to YouTube, if we go to YouTube here, okay. It's always weird to hear your own voice on a video. I don't think we need to hear the sound. Welcome to the city of Phoenix. Yeah, we don't need to hear the sound. All right, so I will mute just for, so you'll notice it's kind of, wait a minute. Oh, that's what you're talking about. How do I get that up? Okay. All right, so you'll notice it's kind of blurry, right? The reason it's blurry is this is actually an 8K video. Right, not 4K, 8K. So it takes forever to process. You actually have to, usually you have to, actually on 360, wow, the internet's really slow in here. All right, well, it's super clear in the real world, if you really watch it. But what's neat about this is, if you're on the virtual reality, like if you click the virtual reality button, you have to watch this on your YouTube app on your phone, or the Oculus. There's a little button that looks like a little headset that puts this into stereoscopic mode. It puts you in like a 3D virtual space. But even if you don't have that, you can still spin around here, and you can look at where we're at, right? So we have, put a little sound on.
Here we are in the low service pump rooms. Low service pumps are responsible for moving water from the lake intake.
But yeah, you can spin around, and you can see, okay, this is the pump room, right? I'm in the pump room. And when you're in the virtual space, you really do feel like you're in the pump room. And then the guys at the Office of Visual Learning are awesome. They did some really cool stuff, not only with, just being able to like put all this together. I think the file's like 100 gigabytes, but it also has spatial audio. So if my face is turned this way and the footsteps are to my left, you hear it on the left. Okay, so that was one thing. The other thing is they put animations in this. Let's see if we can get this.
This treatment plant causing this system.
So you can see some animations going on. And then they put like a little mixer in here. Right, so stuff like that is all throughout the video. But again, if you just want to take your time and watch the video, you can just kind of look around the rooms. Then you go through the whole tour. So it's about a 15-minute treatment plant tour. How many views does it have? That's 1,700 views. Right? So I've been told that a lot of people use this in their classes now, especially during COVID, which I was really excited about. I was like, all right, nobody's going to use this thing. But again, yeah, so if you want to check it out, I have the Oculus here. It's really cool to watch in like the real virtual reality because you can kind of just move around, spin your head. If you guys can see the picture, let's see if we can go down to this picture here. In the background, it's really eerie when I do this in class because the students, they put these things on, they don't know what to expect, and it's like dead silence for 15 minutes. Dead silence because they have headphones on and they're kind of moving around. And it's like, all right. The greatest part is, so it's static, okay? So it's not dynamic. Like I can't walk through the treatment plant, it's static. The greatest part is one of our colleagues, Johannes Westerink, he put this thing on, and the second he put it on, he's like, whoa! And then he's trying to like walk through the space. He doesn't quite get how it works, and he's like feeling around, trying to like touch the, that was pretty funny. All right, so I went a little over here. Obviously, grad students are #1 thank yous, some collaborators, and then some funding and the centers here on campus. So maybe we have like a couple minutes for questions.
How often would you have to replace the Palladium? Or do you have to clean it? Or...
Yeah, that's a good question. What I didn't show was we operated this thing for a long time, and we saw that it stayed steady state for a pretty long time, unless you have something like the bisulfide in there. If you had bisulfide or H2S in your groundwater, for example, you'd probably have to do some sort of oxidation cleaning process. the big question is like, well, what's it like bleach? What's that going to do to the hydrogen layer? So, yeah, do that.
You talked about the thickness, how
Yep.
it can control the rate. How about the packing density? And
Yeah.
Is it directly related to the size, or we have any control of packing density?
So packing density, size, all of that would I would lump into the number of active sites that are available. The more active sites that you have available, the quicker the reaction is going to occur on the water side. And you're pretty much just going to be using that very surface layer of the palladium gel. So you're pretty much wasting, I think in that one, our actual system that we made, we were probably only using 10% of the palladium.
Wow.
Yeah.
You talked about film formation. So for film, you are using directly nanoparticles, or you are forming nanoparticles here?
Okay, you're talking about the layer itself, the catalytic layer? So the question was like, is the palladium on the surface or is it throughout? That's a good question. It's actually throughout. So this is an in situ palladium formation process we have within the hydrogel. So the entire thing.
So what you are using there to reduce it? Because you must be using it in ionic form.
So sodium borohydride reduces ionic form to the particles in situ.
Chemical reduction.
Yeah, chemical reduction, yeah. And that, in fact, we have a patent on this, and that process itself is the patented process of the reduction process.
And one last question. You said the steps of getting this to market. Like, do you see this being something that a general homeowner would buy and put in their well, or would it be more on the big scale?
Yeah, that's a good question. I think if you think about scale-up commercialization of drinking water treatment technologies, I think the first to market area is remediation. So we're talking about like DoD military sites that are contaminated and they have like millions of dollars that they can just throw at it, right? So you're not really concerned about cost. There you just want to scale it up and get it working. The next is probably individual homeowners, right? So like your little under the sink treatment system, right? The last thing is municipalities because they don't have any money.
So they're code for Granger.
Yeah. In fact, I can show you guys if you're concerned. I can show you how to get your water tested, and then also a type of treatment system that you would install.
Well, but if you're a renter, like, I don't know how easy it would be to convince your homeowner to like.
Yeah.
Good luck.
So, if you're a renter, okay, an under the tap RO system that's modular that you can just take with you is the easiest thing. They sell them on Amazon. It's like $200. Yeah, it's just a little system that has replaceable cartridges, and then essentially you'd only drink water. You can bathe and all that stuff with the other water, but tap water would be in that system.
So the regular filters that they have for the water, they're not,
Zero removal. Yeah, so like your fridge filter, the one that you buy and you're supposed to replace every 6 months to a year, that probably not many people do. That's just activated carbon. So that's great for removing like taste and odor and organics, but it's not going to remove nitrate.
Oh yeah.
Yeah.
So this is just taking care of only nitrate, right? Nitrate and
This technology?
yeah,
Oxidized contaminants.
all that.
Yep, perchlorate, hexavalent chromium, nitrate, nitrite, bromate, chlorate, perchlorate, all that stuff, yeah. Yeah, anything that can get reduced.
Okay.
All right.
All right, thank you.
Speaker again.